Welcome back again to the webinar, and sorry for the technical issues we have here. I think it works now, so we can go on. So maybe I will start again. We have the rigid flex boards, we have flex boards, of course, and at last we have the rigid boards, which are the most known PCBs. The difference is in the name, of course, yeah, flex, rigid, or a combination of flex and rigid. But they have a lot of things in common. One is, of course, the functionality because of layers of copper circuitry. This is one function. The other one is PCB is always the operating force behind electronic devices. Yeah. So rigid PCBs, back to them. We call this inhomogeneous system. To connect two PCBs, you need SIF connectors, you need flex jumpers, or you need cables and solder joints. Rigid PCBs are, of course, stable and not bendable. They are reinforced with glass and, of course, mostly green. Yes. If we have a rigid flex board, which we call a homogeneous system, you have two boards which are connected by a flex layer or flex material. You have an identical stack up in the rigid parts, and of course you have a continuous flex layer which is integrated also in the rigid parts. There is some system which we call partially homogeneous system. It's a subsystem, and it's used if you have two different, I would say, rigid stack-ups or PCBs, one with high technology, the other one with lower technology. You can build the one with lower technology with a rigid flex board, have a SIF connector, and connect it to the higher technology board. So that's the main difference for that. Okay, thanks. So here comes our first question to you. What types of printed circuit board systems do you currently use? Did you use inhomogeneous systems, partially homogeneous systems, or homogeneous systems? So here again, some theory. We have different flex solutions. The first one is we have just only one flex layer, which is always on the outside. It's the cheapest option you can have, or the most cost-effective option. And you can use SIF connectors to connect these boards to other rigid boards, or you can, of course, have two rigid boards connected by this flex layer. The next step is you have two flex layers on the outside. Therefore, you can use microwires in the flex area. Of course, not in the bending radii, but you can use microwires to connect the layers. The use of these PCBs, dynamic use is possible. Yeah? If you use the copper only on layer 2 and not on the outside, then you can use it as dynamic for dynamic bending. If we have two layers, it's a flex to install system. You can use, of course, the second layer as a reference for impedance, yeah? And of course, as well as for the 1F or one flex layer, you can use SIF contacts. Next is you can put these two layers inside the PCB. So the PCB again is fully suitable for dynamic bendings. It's again USB. It's symmetrical. This is because of warpage. And of course, you can use different polyamide materials, which is the flex laminate, to come to, I would say, to the best impedance design you need. Though it's not only for trace or for line and space, for line and space, it's also the material which you can choose. Yeah. The next step, and it's just, I would say, the most complex one, you can go from 2 flex layers to 4 flex layers or even more. Yeah. So we have, you can laminate these flex layers together. You can have air gaps between the layers. And you can have 2 or more reference layers for impedance design. So that's a short input from theory. And now Verena will show you some applications. Verena?
Yeah. As Klaus has already mentioned, we can have more than 2 flex layers, and that's exactly what my customer did in this example. you can see here in the camera that we have several, like this. We have several flex cores which are not glued to each other, so they are separate from each other. The big advantage here for our customer is that the flex cores will move against each other, and it's easier to do dynamic bending. This is perfect for IPC USB, which is the dynamic bending. Moreover, this enables a long lifetime for the PCB because the material will not be damaged. And in this case, our customer uses the PCB for more than 20 years. Moreover, we have a smaller bending radius due to the air gap. And so, all in all, the PCB is much better in reliability and for the dynamic bending than a normal inhomogeneous system. Okay. Another application from our customer is a smart sensor where the customer uses 4 layers. Yeah, the PCB is right here. So you can see this is also a homogeneous system with flex between the rigid parts. In this case, the customer wanted a perfect fit in this housing, as you can see on the slides. This perfect fit with the rigid flex PCB enables the use of components on the PCB because otherwise there would not have been enough space in the housing. Moreover, it improves the reliability again because we do not need a connector or a solder area or something like this. And it reduces the costs because we don't need connectors and soldering processes. So you see, the rigid flex in this case is perfect for miniaturization and reliability. The third application that we have here today is a camera, which you can see here. Camera is very small, and this small PCB fits into the camera. So again, the customer uses perfectly the rigid flex technology, combines the PCBs with each other to avoid footprints for connectors and soldering processes. Here in this case, it's also important to have a good impedance or a signal transfer. That's why the customer decided to use rigid flex, because we have a reference layer underneath the signal layer, which has always, everywhere in the PCB, the same distance between each other. And this makes it very good for the signal transfer and also for the camera system itself. Moreover, the prices could be optimized here due to the, as mentioned, to the connectors and of course for the soldering processes. And again, we can see that miniaturization is a big point here and a big goal for our customer, but also signal integrity is very important. Okay, yeah, Klaus, how can we use such fine structures on PCBs?
Okay, yes, of course, everybody knows HDI now, because we have multi-layers, we have HDI technology, and here we have the combination between HDI and rigid flex, which is quite, I would say, a reliable and strong combination. As you can see, in the middle we have the flex part, or on the outside in the picture in the middle, we have wires, of course, plated through holes. We have micro wires. We have micro wires that are filled with copper or with resin. We have stack up with buried wires with 4 lamination on the right side. So there are a lot of possibilities how we can use different connecting types for the PCB. In the picture on the right side, you see staggered wires. Of course, they could be stacked. That's not a problem at all. Yes. So what we want to show you here is an application with all these performance of HDI. It's a camera. It's a communication system. Sorry. You can see here the PCB, how it's built in the housing. Yeah, that's a communication system. It needs to be, of course, with a low weight, yeah, and a small size. So nearly no cable, nearly no connectors. Again, for miniaturization And here, of course, it's wear by people and on the body on the outside. Yeah, it's for rough environment, so it's for reliability again. Yes, and you see here the stack up on the right side again. Especially for reliability, we have staggered microwires, we have the buried wires, and no microwire on the buried wire again. Here. Okay, so but now let us come back to impedance.
Yeah. So maybe some of you already use impedance, or the signal transfer is very important for you, maybe not. Just to keep you all on one level, let me explain what impedances or signals are. So you can see on the left side that we have a transmitter. He sends a signal out. The signal goes through a cable or through a PCB, and on the right side we have the receiver. This receiver receives a signal, maybe not in the right way, then the transmitter sends it out. So you can see the transmitter sent a signal with sharp edges, and on the right side the receiver received a totally different signal. The problem here is that the transfer via cable or via circuit was not good, and that's why the receiver did not get a good signal. You can see this also in the television on the slide. So on the left side we have a sharp picture, and on the right side the picture is doubled. So this is not good, and of course this is nothing for high technology. And that's why a lot of our customers use RIGID.flex PCBs, because here we have the advantage that a signal must not run through different materials. So you see on the stack up on the left side that there is a signal in the flex area, and the reference layers are above and underneath. And you can also see that the distance between the signal layer and the reference layers is everywhere the same in the whole PCB. And that makes it very easy to transfer the signal in a very good way. You can see that we can do a calculation for this, so that the signal that we send into the PCB will be received correctly. In this case, we used 125 microns for the traces, but of course we can also do 100 microns or even a bit lower in the inner layers. And you can see on the right side, we wanted to get 50 ohm, and we received, according to the calculation, 49.74, which is very good. Klaus has already positioned one example here in the camera. You see the PCB, the old system of PCBs, where we have the rigid PCBs, and we have cables here, also with connectors connected to each other. And in this case, the signal will start somewhere over here, and then it will go through the connector, through the cable, down to the other PCB, or in this case, up here, again through a connector, and then to the other PCB. So we have a lot of material changes, which are just not optimal for the signal transfer. That's why the customer changed the layout, and he designed this RIGID.flex PCB, where we have the signal running through the whole PCB in one spot with the same material always, and also with the same distance between signal layer and reference layer everywhere. Okay. So these are the main advantages of RIGID.flex PCBs. But what else have we seen before, Klaus?
Yes. What I will show you is, sorry for that, a conclusion of all the advantages we have heard about now and in the past few minutes. And you can see what's most important. Of course, miniaturization. We talk about HDI or conformal designs, fitting in housings. Yeah. Of course, if space is quite critical in the housing, we talk about finer lines, we talk about microwires, and that's all about miniaturization. Yeah? So, and it's not only in smartphones as we know it in the market, or in very small cameras. It could be even in boards like this. Yeah? So it's in larger boards, because here you can have HDI as well as in the small ones. Yes. So the other one is flexibility, of course. We talk about USB and USA. This means flex to install. This what means just building and housing, and I would say forget it. Yeah, never touch it again. That means flex to install. And we talk about bending. Yeah, this means a lot of bending cycles. I would say without any limit, nearly. Of course, depending on the bending radii. That's the other one, bendability, which always depends, of course, on the thickness of the flex part. If we have 10 layers of copper in the flex part, it's roughly 300 or 400 micron thickness. So you can bend it, but it's not no more flexible, of course. The other one is reliability. Yeah. Verena showed you a camera with a lot of solder joints, cables, and these are all possible failure points, yeah, which we can get rid of if we use a flex rigid board with an integrated flex layer running in the rigid part, out of the rigid part, in the flex part, and again in the rigid part. Yes. So there's no compromise of any usage for these boards. The boards are used in spacecraft, in aircraft, military applications, harsh environment applications. So reliability is a real plus for this technology. Yeah. Another point is signal integrity. Verena showed you an example as well. Because of the material and the copper foil we used, and of course with the compact design, we have a lot of possibilities and options to use these rigid flex boards for signal integrity. Yeah. Even it's the possibility for calculation, it's even, I would say, better and tighter than you have it for rigid boards. Yes, and at least we have the system advantage. So this means system, of course, you have the flexibility in design, depending how many layers you choose in the flex parts, which material you choose in the flex parts, which stack up you choose. So there are a lot of possibilities how you can look on this, on the flexibility of your design. And of course, because of all these possibilities, you have a lot of chances for innovative and compact new designs. Another point is cost saving. If you come back to the PCB, which Verena already shows, the camera system, of course you have the rigid boards, which are nearly the same as you have it in the rigid flex board. Yeah. But you have a lot of connectors. But still, of course, the rigid flex board should be more expensive than all these parts which we use here. But what's most important is you have here 1, 2, 3, 4, 5 different rigid boards. You need assembly process for all these boards. Here, you need one assembly process. You have all the tests, what you needed here. Here you have one test. Yeah? So looking on all these costs, yeah, we think, especially if it's needed for smaller housings, for special applications, these rigid flex boards offer a unique solution for a new or better layouts and electrical performance. Yeah. So we hope we give you a good introduction in this new technology. Of course, if we have we'll have a lot of questions, and we are here to give you a lot of answers. And I hope we have the time for that, or you can come back later to us. Thank you very much.
Thank you.
So now, thank you for the interesting presentation, Klaus and Verena. So sorry for the sound issues. It was our mistake. So sorry for that. I hope now the sound is better. So before we start with the Q&A session, I would like to share the handout from Verena and Klaus, and then you can download it and yeah, a moment. So now you can download it on the right side on the black button. Then I would say we can start with the first question. What is the minimum microWire's pad size that can be used in combination with RIGID.flex?
Yeah.
Okay. So at the moment, the minimum size of the microwire pads is 250 micron. This comes, of course, from the drill diameter which we need for the microwire itself, and the annular ring which is defined by the IPC. So 250 micron is the minimum pad size.
Thank you. Then, next question. RIGID.flex is often used for connecting two connectors on the housing. Often high current handling is needed. Can you talk about copper thickness?
Yeah. 20. Yeah. Okay. So copper thickness depends, of course, on your application. We can offer 80 microns base copper, but also 35 or 70 microns. On the outer layer, we will have a bit more after the plating process, approximately between 30 and 40 microns. Also depends on the process that you need. If you have really high current applications, then we have another very interesting technology that we can show you. So if you have interest or if you're interested in this, please contact us and then we can share some more information about it. But the standard is definitely 80 microns base copper on inner layer and outer layer.
Thank you. Then, next question. Which is the minimum trace width and spacing can be used for impedance traces?
The minimum trace width and spacing is normally 100, 100. Yeah, of course we can go down, but it depends again on the copper which we use. So 75 micron is even possible, but it really depends on the copper we used and if it's on the inner layers or on the outer layers. So there's a different, but 100, 100 is, I would say, the standard, and it's always possible.
Thank you. Then, next question. What is the minimal bending radius?
The minimum bending radius depends again on the material you use and the copper thickness. So you have to look on the polyamide. The thinnest one is 25 micron. You have to look on the copper. If it's on the outside, if it's on the inside, it's not in the inner layers. If it's on the inner layers, you have 80 micron copper on both sides normally. So it depends, but IPC says for the test it's 3 millimeters. We can go down to 1 millimeter, and even you can fold these PCBs. That's what we mentioned, not yet before. You can fold it one time, but never touch it again. But you can fold it one time, but normally bending radius is down to 1 millimeter.
Thank you. Then, next question. We have a lot of questions now. It's very cool to see. Thank you for that. So, next question. It's a little bit. Next question. What is the speed frequency limits per data transfer?
Okay. Normally we do these layouts or these build-ups for RIGID.flex boards with an FR4 material. And we use a polyamide, of course. And with these materials we go up to 5 gigahertz. Yeah. If it's the need for more, you have to use another material. So FR4 doesn't fit for higher frequencies than 5 gigahertz. You have to use a high-speed material which goes up to 40 gigahertz. But this could work together with the RIGID.flex board as well. Yeah, so we can use different rigid or base materials for this technology.
Thank you. Then, next question. Is tempering mandatory before reflow soldering?
Okay. Yeah, it is, absolutely. Because the polyamide, which we use in rigid flexible PCBs, is hygroscopic. That means it will absorb the water of the air around it, and so the PCBs are wet. And that's why we recommend to definitely temper them or dry them before a soldering process. Otherwise, it can happen that you have delaminations, and that's not what you want for the soldering process. If you need some parameters for the drying process, you can find them on our webpage.
Thank you. Then, next question. What is the maximum operating temperature of the flex material?
That's an interesting question. For the flex material itself, it's more than 200 degrees Celsius. Of course, you always use a combination. If you have an FR4 with the TG from up to 150, maybe 170. So operating temperature is not what you can get with the polyamide. You have to look on the FR4. And that's always the same. You have to look on the rigid material and not on the flex material itself. Yeah. So temperature is roughly 150 degrees operating temperature maximum.
Thank you. Then, let's say, next question. What are the limitations of current that can be passed through the flex part between two rigids, and are there clearance difference for a higher voltages in the flex part than on a rigid part?
Good question. Detail, it's quite difficult. Because it depends, I would say, on the voltage itself. What is high voltage here as a question? There are definitely restrictions, but we have to go deeper in data sheets and have a look at it.
Thank you. Then, next question. What is the maximal copper thickness?
Okay. The maximum copper thickness that we use in rigid PCBs is normally 105 microns as base copper, and then we add, of course, the plating. So we have approximately 130 microns at the end. For rigid flex PCBs, we normally recommend to use thinner copper because of the bendability. So if the copper is thicker, then also the flex area is thicker, and so the bending is not that good. Of course, we can do on the flex layers also 70 microns of copper. More is normally not used. In the rigid part, we can also use 105 microns of copper. If that is still not enough, then we can lay in a thick copper part, but only in the rigid area, so that you have even more copper here, up to 800 microns.
Thank you. Then, next question. Is this technology suitable for RF tracing? What is the maximum frequency possible?
We have, I would say, a nearly similar question before. So back again, 5 gigahertz is fine. If you need more, of course, you need a different rigid material, and therefore, of course, this one is even higher and is better fitted for RF than the polyamide itself.
Then, next question that can I answer. Are recordings available after the live stream finishes? Yes, you will all receive the recording and the presentation in the next days via email. Then, next question. Is HIL surface finish possible?
Okay. Yeah, HAL is possible. Normally, we recommend to use incl as a standard because HAL has very high process temperatures, which are not that good for the bendability of the PCB, and that's why we normally use HAL only for flex parts, which are on the inner layers, so that the flex material is protected during the process. If you want, we normally don't do it for flex on the outer layers. So here it's also good to use incl, which is also very good and reliable surface.
would a 100 ohm flex work?
I think it means 100 micron thickness of the polyamide. Of course, it fits quite well. Of course, you can calculate bending radii, which is a bit higher than for 25 micron polyamide foil, of course, but it fits for bending quite well. No problem.
Thank you. Then, next question. This one. Is it also suitable for power applications? What are the restrictions?
Shall I? Yeah. Okay. Yeah, it is possible to use it for power restrictions, but of course you have to calculate the copper section that you have here so that the currency will not damage the circuits. As mentioned before, we can also use thick copper parts in a part of the rigid area so that you can use real high power applications also in combination with rigid flexible PCBs.
Thank you. Then, next question. Are the flex stake-ups UL 49 listed?
Yeah, listed. Yes, I would say yes and no. It depends always on the material which we use. Würth Elektronik CBT has UL for FR4, 150, 135, 170. We have UL for high-speed materials in combination with high-speed materials. So there are a lot of UL 94, but it depends on the UL class. Is it V0 or V1? So it depends there, but we have a lot of different UL possibilities and listenings for UL.
Thank you. Then I think we have no more questions left. Would 4LX 100 ohm CU with flex work? Vier line, yeah. Sorry, vier line, yeah.
We not recommend to use this combination because we have a very high thicker amount in the flex area. And so the flex is very thick and also the bending radius has to be very big. And that's why we not recommend it. Normally, the polyamide material has a base material of 70 microns base copper. So 100 is not really common and normally not used. As mentioned before, it makes sense to use the thicker copper in the rigid part and then connect it to the flex part so that you can also use the copper in the rigid part or the thick copper in the rigid part and use the flex more for the signals.
Thank you. Then I would say we are finished with our session today. When you have one more questions left, you can write in the chat and then Verena and Klaus will answer them via email in the next days. Then I would say thank you for your interesting presentation and for the answers of the questions. And then I would say I hope you enjoyed it and hopefully you see us on the next session of the Digital Redays. I would say thank you and goodbye.
Goodbye.